Hi everyone, my name is Balazinska and I'm very happy to be here today and have a chance to tell you about Vocal, a system that we are building in the Allen School at the University of Washington in collaboration with the Microsoft Gray Systems Lab. And Vocal stands for Video Organization and Interactive Compositional Analytics. Vocal is a system for video data management, and there are many trends coming together that are really pushing the demand for these kinds of systems. First of all, cameras are really deployed everywhere in our environment. Most of us have phones and kind of commonly use our phones to record different videos. There are also cameras in our cities, in nature, cameras on top of self-driving cars and in other locations. Additionally, once we record all of these videos, we now have access to increasingly affordable large-scale storage, whether it's in one of the public clouds or on hardware that we can all purchase. And finally, also very important, advances in computer vision are allowing us to ask really complex questions and really extract a lot of interesting content from those videos. And those really three trends together is what is pushing the demand for novel video data management system. As a result, our community and also neighboring communities have really developed a lot of exciting systems and techniques across the stack in this space. And this includes some of our work from the database group in recent years. But in spite of all of these great advances, in this talk, I'm arguing that there are several critical needs that remain unmet, and that is the goal of the Vocal system. So first of all, in many scenarios, when users start with their data, the data is actually dirty. As one example, we are collaborating with scientists from the College of the Environment, and what they have done is they have put cameras on collars that they attach to deer in the wild. The deer walk around with a collar and a camera for a couple of weeks, and then the collar is programmed to detach and drop on the ground, and the scientists can pick up the collar, extract the videos, and they have access to weeks of videos from many deer. And the problem is that chunks of this video correspond to times where the camera was covered by snow or accidentally recorded data at night. So they definitely start with video that is hard to use because of these kind of dirty fragments that need to be cleaned. Second, in this domain, as well as in others, there are no pre-trained models that we can simply apply to answer queries on the video. For example, here we have 4 screenshots that show different activities of those deer in the wild as captured by these egocentric cameras. So the first screenshot, for example, shows a deer traveling, which is mostly just pictures of trees and grass. Same thing for a deer that is bedded. We mostly see pictures of the sky and of trees. Foraging is a little bit better because we actually see the snout of the deer, but it's still not obvious, and there aren't existing models that we can directly apply. And finally, users don't want to only find kind of simple activities of those deer in the wild. They want the ability to answer complex questions. For example, finding fragments where a deer was foraging and then multiple deer were traveling together. And these queries are not only difficult to execute efficiently, but they're actually very difficult to express. So this is what the Vocal system is trying to answer. We are working with users end-to-end, starting from their dirty, large-scale videos all the way to answering complex queries on top of those videos. So in contrast to prior work, Vocal makes 3 contributions by removing 3 main assumptions. We do not assume that the data is clean. We know that we're starting with dirty data. We do not assume access to pre-trained machine learning models for this domain. And we do not assume that it is easy for users to express complex queries in a declarative fashion. We really want to support users end-to-end through all these different tasks of video cleaning, exploration and labeling, and compositional query processing. We already have a prototype of the Vocal system, although this is very much a work in progress, and this is a vision paper. So this is really talking about the work we are currently doing and in the database group in collaboration with the computer vision group. So our prototype can be seen here, a screenshot of it. Users can load their videos, and they already have the ability to scroll through video fragments. We showed the first frame. If you hover over the videos, you can see kind of the video playing. So the user can select videos, start to annotate the videos with different activities, and so on. So given this initial prototype, to kind of address this first issue of data cleaning, we allow the user to identify dirty fragments, right, dirty video frames, and label them for us. We then build a model that uses very simple features around like colors and motion to detect and automatically clean those dirty video fragments. We find that this is not a very hard problem because typically dirty video looks quite different. As I mentioned, often it corresponds to cameras being covered by snow, cameras filming at night, so reasonably easy for the user to give us some examples of dirty video and for the system to build a model. More interesting is how can we go from that to actually labeling the different activities. So now that we have clean data, what the system is doing, it's quite overwhelming for the user to look at weeks and weeks of dear video activities. So our system starts by clustering the videos, and there are different kinds of features that we can use. And this is actually one of the research questions. Should we be using simple features, easy to extract, invest more resources and time to get more complex features? Given a cluster, our system will select a cluster and show to the user. The user can then provide feedback and say, these fragments of the videos actually do not belong in the same cluster, or these fragments do indeed belong to the same cluster. They can add labels. And another interesting research question is around these, what kind of feedback should we be asking the user for, and what are the implications of the different kinds of feedback on the speed with which we can eventually label and all the videos and build good models for this new domain. Given the feedback from the user, we can recluster the data and kind of update the labels, propagate the labels to other video fragments, and use that to then train domain-specific models. And this is, of course, an iterative loop. Once we have the updated clusters, we can once again pick another cluster to show to the user, and you're exploring different active learning techniques to determine which cluster we are going to show to the user. The paper shows some of our preliminary results around this work. In particular, we have explored different types of features, starting from basic features like motion and colors, all the way to using features from an existing pre-trained model. Here we have tried a pre-trained model on human activities, applying to this domain to extract some features, all the way to using self-supervised techniques to develop really extract features specifically for this data. As the figure here at the bottom of the screen shows, for some activities like the deer being bedded versus traveling, they're pretty easy to distinguish with all of these features. But in some cases, like distinguishing between traveling and foraging is actually difficult. The self-supervised learning techniques perhaps perform a little bit better, but even then this remains kind of a challenging problem. Once we have labeled the data and we can build models for this domain, we can now allow the user to ask more complex queries. In this case, I'm going to actually change to another example from another domain because it's easier to explain. But here we want to find video segments when cars turning at intersections are turning while pedestrians are crossing. This might be in the context of determining if these kinds of turns are causing hazards for pedestrians. So this is clearly an application from the traffic monitoring domain. The challenge is that there is no model available to find this desired activity directly. We could ask the user to manually label fragments to build such a model, but that's A, tedious. B, there might not be enough examples in the data to actually build the model, and it definitely takes a significant amount of time. We can try to answer this query from kind of combining predicates over simpler, just objects being detected. But this is actually incredibly hard because if you think about even in this simple example, the car might be, turning left or right. So there are many combinations of, there are actually many kinds of video fragments that are going to satisfy this query. At the same time, there are also important constraints that are easy to forget. So we have to make sure the pedestrian is crossing at the same place in the intersection as the car and is kind of close in time to the car. And of course, evaluating the query is also another challenge. So the approach that we are taking in Vocal is we have a data model, and the data model is built on the notion of a scene graph from the computer vision literature. So each frame has objects and relationships, and the query that the user articulates will express predicates on top of those scene graphs. So I can specify predicates on the objects, on the relationships, and also predicates on kind of the scene graphs across time from frame to frame, including different region predicates. But of course, we don't want the user to specify all of this manually. What we want is for the system to learn the query specification based on user feedback. And we do this as follows. So the user starts by looking at the video, and they can express just a partial query. So they can perhaps only tell us the objects they are interested in or the region in the video they are interested in. Once we have this partial query specification, our system will find frames or video fragments that match the partial specification, ranking based on how well it matches, and then showing them to the user. The user can then tell us at least, are these positive or negative examples of the event they are looking for, but it can also tell us more. The user can perhaps indicate bounding boxes around the objects of interest, indicate relationships they're interested in, and otherwise provide feedback on the fragments we show them. Given this feedback, our model can now start to learn the different predicates for the user query and use that updated understanding of the query to show the user the next set of video fragments of frames. We show again some preliminary results in the paper. In particular, we find that using this kind of iterative technique with learning the query specification over time can really accelerate the task of finding all the events in a video fragment compared to randomly selecting frames, or even randomly selecting frames that contain at least the objects of interest. So in summary, Vocal is a system for video data management. We support users end-to-end from the task of data cleaning all the way to the task of complex query processing. We work with new and uncommon domains that don't already have existing machine learning models. We provide interactive data exploration and cleaning, support for data organization and labeling to build these domain-specific models, and all the way to enabling this interactive complex query processing on the final resulting data. Thank you very much. I invite you all to read our paper and also visit our website. Thank you.